good evening, everyone. I'm Calvin Joseph, and today I'm going to conduct a summary session for the course Electrical Measurement and Electronic Instrumentation, which was taught by Professor Abhishek Chatterjee. So this course was a 12-week duration NPTEL course, and it has various sections out there. So it has electrical measurement instruments like such as the ammeter, voltmeter, wattmeter, which are just a small amount of stuff. Then also how errors are, how important it is that when we do measurements, we want the measurement to be accurate. So in that, to quantify it, we use errors. Then also, sir touched briefly regarding digital electronics, and also sir did a lot of theory he taught regarding analog electronics. Okay, so all these I will consider in this session. So this is going to be only a 1 hour session, and I have to summarize like 12-week content. So it is like approximately I have to spend 5 minutes to summarize 1 week's content. So I like what I thought of doing is like to just tell the main topics, main formulas, to give it to you, like to write it so that you can remember, try to understand it. Okay, and if you have any doubts, any queries, you can stop me and you can ask me. Okay, but the goal over here is not to teach content. The goal over here is to just revise important concept, like to just bring up those formulas into your mind, so that once I make these notes, etc., you can use it to prepare for your exams. Okay, so these notes will not be a substitute for you. Like you have to refer to your notes and also study, but this is like just to give you a solid revision. Okay, so I'll start. Okay, so this is summary session which I'm going to take, and we will start with week 1. Okay, so in this week, sir taught about various types of instruments. One is the PMMC. PMMC stands for Permanent Magnet Moving Coil. Okay, and as in all these instruments, there's something known as a torque. They generate torques. Okay, there are two torques. There's a deflecting torque, and there is something known as a controlling torque. Okay, two types of torques are there. So controlling torque is mainly from the spring, and that is given by K into theta. K is the spring's constant. Deflecting torque will change depending on the instrument. So for the PMMC, the deflecting torque is given by BANI. Okay, in steady state, that should be equal to a controlling torque. So you get the formula BANI is equal to K into theta. Okay, so this is the formula which you have to use. Various things will be given. Another thing to note down is sensitivity. So sensitivity is for the deflection per current. Okay, so what will that be? That will be BAN upon K. Okay, so these are some things you must remember. Another point I'd like to stress is, since you're going to give the exam soon, you should be very careful in what units you're using. So I preferably solve sums in SI units. Okay, all this micro, milli, all that I converted to the actual unit. Okay, all these things also you must know, because these things might create errors. And another thing is you must read the question very carefully. They may say find the current. You may just find the current in ampere. But the question may ask you to write down the current in milliampere. So accordingly, you must make the proper conversion. Okay, so those parts you must be very watchful and careful and vigilant while doing the sums. Okay, so next type, so PMMC will measure DC. It will measure DC quantities, and so it will give you the average value. It will give you the average value of your voltage or current, whatever it is measuring. Next instrument we have is the electrodynamic instrument. Okay, so there's a moving coil and there's a fixed coil, etc. And it depends on the relative, magnetic inductance. So here the formula is given by I square into dm by d theta. Okay, this is the deflecting torque, and at steady state that should be given your controlling torque. So that means the I square dm upon d theta is equal to k into theta. So here your deflection theta is proportional to I square. Okay, so in that, when it tries to average out the result, this will give you the RMS value. It will give you the RMS value of your current. Okay. Next is the moving iron instrument, MI. Moving iron instrument, in which your torque is K into I square. Okay, some K1 into I square, which is deflecting torque. The controlling torque is K2 into theta, let us assume. So that's why K1 into I square should be equal to K2 into theta. Here again, you will get the RMS value. So this is PMMC is used to measure DC, and electrodynamic and moving iron measures RMS value. So another thing is this is a linear scale. This gives a linear scale. While electrodynamic and moving iron, they give you a non-linear scale. Okay, because of this square term, which is present. So these things, this PMMC, this electrodynamic, and this moving iron, mostly are used to measure currents. Primarily, they actually measure the current flowing into the instrument. But there's another instrument known as an electrostatic instrument. In this, the torque which is generated is actually given by half dc by d theta into v squared. Okay, this is the formula. And that again is equal to k into theta. So we know capacitance is A into epsilon by L. So epsilon and L are constant. So it is only this thing which is varying. Only this one will vary. Okay. So the common area between the two plates, that is this A. So that you have to look at the sum, etc., and you will be able to understand. Okay, so this is the brief summary of what was taught in week 1. So now I will proceed with week 2. Week 2. Okay. So here, sir taught about ammeter, voltmeter, etc. So one of the very important questions, or one of the favorite questions is, I have a PMMC instrument. Okay, I have a PMMC instrument. It has a full scale deflection current, let us say, of 10 milliampere. Now, I want to use it to measure current from 0 to 1 amp. Okay, or say I want to use it to measure a voltage of 0 to 100 volt. Huh? And this PMMC instrument will have some internal resistance, let us say 100 ohms. Okay, so all these questions, what you are going to use the PMMC instrument, and you have to connect some resistor in the series or parallel, so that to be able to extend the range or use it for current or voltage measurement. Okay, so now if I want to use it as an ammeter, so you must understand, as an ammeter means ideally the ammeter's internal resistance should be 0 ohm, but practically it's just some finite value. So what you do is you have this PMMC instrument over here which measures current. PMMC instrument has some resistance. You will connect a resistance in shunt. R shunt you will connect. So this overall thing will become your ammeter. So this R shunt you must select it in such a manner that you can extend the range, that you can increase the range. So that means some current, maximum current here will go 10 milliampere. This can carry a current. If this current has to be 1 ampere, this current is 10 milliampere. So this current should be how much? 990 milliampere. Okay. This RM is how much? RM is what I take? RM is 100 ohm. 100 ohm. So this voltage drop will be how much? 100 ohm into 10 milliampere. It is 1 volt. Okay. So that means your R shunt will be equal to 1 volt divided by 990 milliampere. Accordingly, you will get what is the value of R shunt which is required. Okay, so this is a very common question, very basic question which you guys know. I'll just do a demo. Next, I want to use it as a voltmeter. So remember, for a voltmeter, the internal resistance ideally should be infinite. Infinite ohms, it should be the internal resistance, but practically it is not possible. So what you do is you have this which measures up to 10 milliampere. You have this resistance of your galvanometer, and then you connect the resistance in series. Okay, such that what will happen such that you can measure between 0 to 100 volt over here, and the maximum current which will flow over here is 10 milliamp. Okay, accordingly, using KVL, you can find out what is the series resistance which is required. Okay, so this is the part of how you do the ammeter voltmeter. Next is, so till here, does anyone have any doubts, any queries? You can ask me. Okay, so these are very basic things, so I trust that you know it. I'm just giving you a brief recap so that it will just register in your head. Okay. Next is this PMMC instrument is a very useful instrument because it is like very sensitive. It has a linear scale. All these advantages are there, but it cannot measure AC. It cannot measure AC. So if I want to measure AC measurement, what do I have to do is I have to use a rectifier. I'll have to use a rectifier. So suppose I have a AC input voltage over here. This is my VAC. What I do, I place a diode and I place a resistor here. Okay. And over here, I connect my PMMC instrument. So over here, suppose this is my AC quantity. This V output will be positive cycle will be there, negative cycle will be 0. Sorry. Then again it will be there, negative cycle will be 0. So this is my V output, this is my VAC. One important thing, formula which you can derive in the exam, I'm not saying you cannot derive, but it is important for you to know is if this your input AC voltage, it has a maximum value, let us say V max. This voltage also will be V max. Okay. But what is the average value of this? What is the average value of this? So for a half wave rectified signal, if I have a half wave rectified signal, my V output average will be V max upon 5. If it is a full wave rectified signal, then my V output average will be equal to 2 into V max upon 5. So that signal would be something like this. Would be like this, like this, like this, like this. Both in the positive and negative cycle, it gets rectified to a positive value. So the average quantity, okay, this average is given by 2 V max upon 5, and this average is given by V max upon 5. Okay, so this is a formula you can memorize and keep so that you don't need to derive it again in the exam. But if you forget, you can derive it. Okay, so this is used for half wave rectification. For full wave rectification, we use this one. And the output is taken from here. This is where we connect the output. And this is your input. And over here you connect your voltmeter. Then it's your output. Okay. So this for full wave rectification, this is for half wave. Right. So now we proceed to V3. V3 is related to errors. Right. Now what is error? So there is suppose some resistance R. Through it is true value is 100 ohm. But the measured value comes out to be say 100, 1.2 ohm. This is the measured value. So what is the absolute error? Is the measured value minus the R actual or true value. So that is what 1.2 ohm. But now 1.2 ohm or 1 ohm, how do you know that error is lots or less? Okay, like see, suppose a rich person is there. If he loses 100 rupees, it is not a problem. But if there's a poor person, if he loses 100 rupees, it is quite a big problem. So how do we know what the seriousness of that error or the problem? So that's why you use something known as relative error. Like percentage, okay, first is that you go to relative error. Relative error is given by the absolute error upon the true value or the actual value. So that is 1.2 ohm divided by the 100 ohm. Okay, so that is like 1.2 upon 100. Then what is the percentage relative error? Percentage relative error is what? Relative error into 100. So that is 1.2%. Now there is a doubt. We don't know what is the actual true value of something. How do I know that the true value of this resistance of this is 100 ohm exactly? I don't know. So it is unknown. In that case, instead of true value, we must use measured value in the denominator. Okay, that is another case. Another thing is the resistance is measured using something known as a Wheatstone bridge. Wheatstone bridge. Okay, that it will have like say R and P, S and Q. Okay, P, Q, and S are known, R is unknown. And there will be some galvanometer here. Okay, and there will be some voltage which will be applied. So the current to the galvanometer should be 0. Then the bridge is said to be balanced. So in the balanced condition, what happens is the current to the galvanometer is 0 ampere, and your R into Q is equal to P, this is P, into S. So your R is given by P by Q into S. Okay, this is the value of R in terms of P, Q, and S. So your R is your unknown, P, Q, what you know, and S also is what you know. So what they do is usually they keep P and Q to be fixed, and you will vary S. S you will vary slightly here and there. You will keep on varying it such that there comes a condition where the current IG is 0, and then you calculate what is the value of R using this formula. Now, theoretically, I found out what should be the value of R. But how accurate is the value of R depends on the percentage error in P, Q, and S. Suppose the percentage error in P, relative percentage error in P is 1%, the percentage error in Q is 5%, and the percentage error in S is 2%. Then how will I know what is the true value, this value, that value, how much is the error in R? That is problematic. So what a simple formula is the percentage error in R is equal to the relative percentage error in P plus the relative percentage error in S, both are in the numerator, plus the percentage relative error in Q, which is in a denominator. In all cases, it is plus. So it is 1% plus 2% plus 5%. So the effective percentage relative error is 8%. Okay. So from this, you know that it is these things should be as accurate as possible. And I've just given an example how the accuracy will depend on the errors in the PQ and S, and how the error propagates. How the error, even though it is in one is a numerator, one is in a denominator, their effect is equal. Okay, their effect depends on the value of their relative. It's not that if it's in a denominator, it gets subtracted. Okay. Then another important instrument is the wattmeter. The wattmeter is used to measure power. It is used to measure power, to measure the average power, etc. So power is given by what? V into I into cos phi. Phi is the phase lag between the voltage and current. So to measure it, what is required is you need the voltage information and you need the current information. So what instrument is used is the electrodynamic instrument. Electrodynamic instrument torque is actually given by I, which is actually given by IF into IM into DM upon dt. The earlier formula I considered that the fixed coil and moving coil is the same, but now I'm using different currents are going to the fixed coil and moving coil. And to the fixed coil, it will be like something related to voltage by R, and this will be this I, okay, into DM by dt. So these will be used. So now your wattmeter will have this terminal, which is your pressure coil, and this terminal, this is your current coil. Okay. Suppose I have some resistance R, and I want to measure what is the power which is being drawn. So I'll connect this is my current coil, and this is my potential coil, and this is my input VT. Okay. This is my wattmeter. So there are certain errors which come because this is the current to the current coil. The pressure coil measures the actual voltage. Okay, and this is, let us say, the current I. But there will be some small current drawn by the pressure coil. And this is what leads to the error. This is what leads to the error in the measurement of the wattmeter. Okay, so there's something known as a compensated wattmeter. They use some other winding, etc. to minimize the error. But for the time being, we can tell you, so you can understand this. So, any questions till now? You want to talk? Okay, so there are no questions. I'll proceed further. So I know I'm going at a quite a fast speed and not as how we usually go, but this is because it's a summary session. I have to cover a lot of things. So now let us go to the week 4. Okay, in the week 4, energy meter has been taught. So energy meter connection is same as wattmeter. Connection of the energy meter is same as the wattmeter. The errors also are there. Then another thing was taught is known as the DC potentiometer. In that you have an infinite not infinite resistance, you have some resistance over a very long length and you will connect it over here. So there's some voltage. Vx will be applied. And there is some known voltage source. We know. Okay. And you will connect it like this. So depending on this length L, you can determine what is this Vx. Okay, Vx can be determined. Okay, it is on these lines. There will be some resistor, etc. will be there, but it is similar. So you have a known voltage source or a fixed voltage source, and based on that, you can find out the estimate what is this Vx. Then there's something known as a Kelvin-Varley potential divider. Okay. So this also is similar to a DC potentiometer. So it will have some resistors R1, R1, etc. they will have one more R1. Okay. Then this will be between two R1. Okay, it will be between two R1. Okay. Then it will go to some R2, R2, on and on. Again, there will be some, say, 11 R2. So 11 R2, 11 R1 will be there. Then again over here, there will be certain thing which is between two R2, and that will go to R3, R3. So let us say it goes to the R3 over here and will come. Let us say it is the final stage. Okay, final stage. So what formula you must remember is your 10R3 should be equal to 2R. And your 10R2 should be equal to 2R1. Okay. So over here there will be 11 resistors, 11 resistors. In the final stage, there will be 10 resistors. So this formula is important for you to remember for the Kelvin-Varley potential diagram. Then also, sir, touched upon AC potentiometers, etc. There's coordinate potentiometer, there's a phase potentiometer, etc. to read the phase and all this. But these are important topics I'm touching over. Next is weak file. Here, sir taught about AC bridges. Okay. So another important concept which sir follows and this is he encourages you to he doesn't force you to mug up or to remember the things. When the examination he will accordingly give you questions. He wants you to look at the circuit, understand what concept it is there, what concept has to be applied in that circuit, and then you can derive or you can find a condition. It's not like you have to memorize that this circuit means this formula, this is the Wayne bridge network, this is the Voltmeter oscillator, etc. You don't need to remember each and every circuit or each and every bridge. Okay, you just need to look at the circuit, try to understand, use the known standard formula, and then try to derive the answer. Okay, so AC bridge is a bridge. Okay, which is used to measure. It can be used to measure impedance, or it can be used to measure frequency. So let us say there is a bridge of impedances out there. So one way to remember it is the opposite ends having multiplied. So that will be Z1 into Z4 should be equal to Z2 into Z3 under a balanced condition. Okay, balanced condition. So in our Wheatstone bridge, which we saw earlier, it is PQ equal to RS something is there. And that is purely a resistor. So it is just magnitude. But when you come to AC bridges, both magnitude, that is your Z1, magnitude Z2, Z4 should be equal to magnitude Z2, magnitude Z3, and your angle of Z1 plus angle of Z4 should be equal to angle of Z2 plus angle of Z3. So there are two conditions. There's a magnitude condition which has to be satisfied, and there's a phase condition also which has to be satisfied because it is a phasor quantity. It is no longer DC, it is an AC quantity. So there's magnitude and phase. So this is something which we have to look into. It is very easy, you have to derive it. And another part which I want to stress upon is phasor quantity, let us say Z1. It will have some 10 plus 20J. Okay, this is the value. And now let us say your Z2 or your Z4 is like 1 plus 4J. Okay, so now what do you do? It's like you cannot directly do Z1 and Z4. Okay, I'm sorry. This is not angle because it is Z1 bar, Z4 bar, because it's a phase. Okay. Now you cannot directly multiply it because you're using the gate calculator. It doesn't have this phase plus J. Imaginary operator doesn't have. So what we have to do is we have to do Z1 bar or Z4 bar. What you can do 10 plus 20J. Okay, 1 plus 4j. So this is very practical. This is what you will actually be solving. That's why I'm showing to you. So this will become what? 10 plus 40j plus 20j minus 80. So that will be equal to minus 70 plus 60j. This is the way you must solve it. Okay. And then if you want to write it, this is what is known as the coordinate form. And if you want to write in the polar form, it will be square root of minus 70 square plus 60 square angle of tan inverse 60 upon minus 70, etc. So you should know to do all these if it is given required in the exam. So now another part is practical inductor. You have what is known as a practical inductor. Let us say this is my L. It will also have a small resistance in series because it is a coil and you're winding the turns. So in that wire, there will be some resistance. So that resistance comes in picture. So the quality factor for an inductor is given by omega Ls by Rs. Then you have a practical capacitor. There's a capacitor C in which it is the current which flows actually is just displacement current in the capacitor. If you guys know. But then, and you guys know because yeah, you guys are studying this. Then we will connect a parallel resistance also will be there because there will be some leakage current. So your dissipation factor or your badness factor is given by the formula 1 upon Rp omega Cp. Okay, so this is the way to look at it, and I'm writing the main important formulas so that you can refer to this and you can proceed. Okay, and from these you can derive further. That's right. So next is week 6, where it is about instrumentation transformers. So as you guys are becoming electrical engineers or already electrical engineers, there are two basic electrical quantities which you always deal with. You deal with current and voltage. Okay, from that you derive power, from that you can derive energy, all those things are there. This is secondary. The main thing is your current and your voltage. So now, in all these transmission and distribution lines, high voltage lines, etc., because the current and voltage is very high, what they use something known as a current transformer and a potential transformer. So they use what is known as a CT. CT is a current transformer. And PT is known as a potential transformer. Okay. So current, basically what they are also transformers. There are some turns N1, it has some turns N2. This is your V1, this is your V2, this is your I1, this is your I2. So what we know, I1 into N1 should be equal to I2 into N2. Similarly, V1 upon N1 should be equal to V2 upon N2. This is the ideal condition. So in a current transformer, what will happen? Your current I1 will be very high. And your current I2 should be lower. So that means what? Yeah, N1 should be less than N2. So N1 should be less than N2 for a CT. And in a potential transformer, what happens? Your V1 is very high. Your V2 is very low. So that means your N1 must be very high and your N2 must be low. So here N1 should be greater than N2 for the potential transformer. So potential transformer is basically a step down transformer. And CT is basically a kind of like a step up transformer. Right? So I'd like to say, so this session is being conducted on Zoom and I don't have the paid version. So these sessions are limited only to 40 minutes. So in 2 minutes, this session will stop, it will end. And then immediately after that, I will restart the meeting. So you can again rejoin immediately. Okay. So don't get surprised suddenly you're kicked out of the meeting and everything. It will again start, and the same link you have to again join this meeting. So this is for the CT and PT. Another thing which I'd like to highlight is the errors. There are certain errors which creep in the CT and PT. Because you know what is a transformer? It has some resistance, inductance. It has a RC. It has some XM. Then you have your ideal transformer. Then you have this. This is your RP primary. This is your primary inductance, secondary resistance, secondary inductance. This is your V1. This is your V2. This is your I1. This is your I2. And this is your number of turns N1. This is your number of turns N2. So these things cause errors. They are the ones which are causing errors. Okay. So there are two types of error. One is the ratio error. Another is the phase error. Both these errors happen because of these currents. Right. So one more important one thing to remember is the CT. It should never be open circuit. And then a PT should never be short circuited. So these are few important things which you must make sure are followed. These are practical things. Okay, so in the questions also, these questions will be asked true or false, etc. So please keep these things in mind. Next, after this, taught things regarding digital electronics. We'll taught about various like SR flip-flop, T flip-flop, D flip-flop, etc. So that's talked about. Okay. So just the SR flip-flop diagram I will draw. It is made of two NOR gates. Each two, this is two bar. This comes here, and this is your set. This comes here, this is your reset. Okay, this is your SR flip-flop. It like takes feedback, etc. This is kind of the digital logic. You guys already know what is AND gate, OR gate, etc. This is made using a combination of these gates. You have feedback process incorporated. T flip-flops is used for binary counter is made using T flip-flops. Okay, then binary ripple counter was taught, and how do you reset it once it reaches a particular value into the stop here. And why do we use a counter? Counter is like exactly what you must understand as a from a broad way, from a large way. You look at a counter is it will count the number of clock signals. Number of clock signals it will count. It will count, and this is like the standard part. You give like this, like this, like these are your clock signals, which are counted. Okay, this is your clock. So your counter will go from 1, then 2, then 3, then 4, 5, 6, 7, 8, 9, 10. Like that, basically how your counter will change. So it is basically not counting. And then it should also have the provision to be reset. Suppose it reaches 20. Then I want it to stop. Then I make it again back to 0. Then again we count 1, 2, 3, 4, 5. So all these provisions should be there in the counter, the ability to reset it and the ability for it to count and should be able to store that value. It will be stored in a digital value, and then we can access it and find out what is the value in the counter. So this is there. Okay, next we will go to analog electronics. These are a stored. So this comes in week 7. So, okay, we'll have to go to the next page. So till here, any doubts, any queries? I'll just share these links. So I have posted the Drive link and the YouTube channel link. So once this session is completed, then I will convert this into PDF and I will put it on the Drive so that you can access this notes and you can refer to them. And then YouTube link also I've added my YouTube channel link where I will, after editing this video and combining watching etc., I will upload this video there for which you can recheck. Okay, so both things I have kept. The provision is there, so that you can go back to it, and if you've not understood something or something you missed because of poor internet connection, all this provision is provided by NPTEL. Okay. So next is analog electronics that we will consider what is known as a difference amplifier. So the circuit of a difference amplifier is given like this. This is op-amp. We have some plus V supply, minus V supply, and this will be output. This is your R1, this is your R1, this is R2, which is connected to ground. This is R2, this is your V1, this is your V2. So, in an op-amp, there are op-amp questions will be asked a lot because it was taught a lot. And how do you identify, how do you solve the sum? Okay. So one thing to note is the feedback negative? You must see whether there is negative feedback. If there is negative feedback, then you apply a concept known as virtual short or virtual ground concept. What does that concept say is that when there's negative feedback, these two can be thought to be virtually connected. So if they're virtually connected means they are the same potential. So let us say this is V minus, this is V plus. So your V minus will be equal to V plus. Right? So this is a concept of virtual short which is very useful for us to solve sums. And if you use this concept of virtual short, then you will get your output voltage to be equal to R2 upon R1 into V2 minus V1. Between the positive and negative terminal, what is the difference in that voltage is applied. That is why this is known as a difference amplifier. Okay. So the virtual short concept is very important. So when you look at a sum, you will not know what sum it is. Okay? You will not know whether it is a Schmitt trigger, whether it is a comparator, whether it is an amplifier. How you must identify is you must see the output. That is, this is your output is being fed back to the negative term. Hence, it is negative feedback. And when it is negative feedback, then you can say that you can apply the virtual short concept and you can say that V minus is equal to V plus, and you can use it and you can derive the output equation. Okay, so this is for the difference amplifier. Next, we will consider for what is known as your. So after the difference amplifier, you have your inverting and non-inverting amplifier. So over here, this is your R1, this is your R2. For simplicity, I'm not showing this V supply minus V supply, but they are there. Without that, your op-amp cannot work. So op-amp is an active device. It needs a power source. Okay. So in a non-inverting, amplifier, okay, I am applying my input voltage at a positive term, but the feedback is negative. So what is my V output? My V output will be equal to 1 plus R2 by R1, which is my V. This is for the non-inverting amplifier. This is the logic. Next is I have what is known as a inverting amplifier. So inverting amplifier means the input is applied to the negative terminal. positive is connected to ground or it can be connected to potential. The output is your R. So V output will be equal to minus RP by R1 into V in. Okay. So these things also I had taught in the week 7 session, and it was also taught LT spice demonstration also I provided for this inverting non-inverting. So if you want, you can refer to this and you can understand like how actually this is practically how it looks like. So this is an inverting non-inverting amplifier, and an amplifier is used basically to increase the level of a signal and to act as a buffer. So what is a buffer circuit? Buffer circuit is when this is your V input and this is your V output. So V output is equal to V in. So this is known as a buffer. Right? So next we will go to V8. This basically deals with Schmitt trigger. Schmitt trigger works on a concept of positive feedback. So it can take only two options. It can either be plus V supply or minus V supply. It can have only two values, two stable values. So one is my inverting Schmitt trigger. Minus plus. Here it is mandatory for me to demonstrate these colors. This is my V output. Let us say this is my output. And this is my R1. And this is fed here. And this is my input. Okay. This is the why here it is output signal step down. It's taken to the positive terminal. So that is why it is positive feedback. Okay. And then there are something known as bands. Okay, let me write down the formula. The upper trigger point is given in this case is V supply into R1 by R1 plus R2, and the lower trigger point is actually minus V supply into R1 divided by R1 plus R2. And how does it work is when the input voltage crosses the upper trigger point, then it will go low. Then when it goes less than low trigger point, it will go high. Okay, let that be change the output. So this is for your non, and this is actually an inverting Schmitt trigger. This is an inverting Schmitt trigger. There is another circuit which is known as the non-inverting Schmitt trigger. This is your plus V supply. This is your minus V supply. This is connected to the ground. This is your R1. This is your V in. This is your R2. This is your V output. So in this case, the upper trigger point is given by V supply into R1 by R2, and the lower trigger point is given by minus V supply into R1 by R2. Okay, so this is the formula for the non-inverting Schmitt trigger, and this is the formula for the inverting Schmitt trigger. You can have to derive it in the exam. So I am just giving it, compiling it and giving it to you here so that you can easily read to the line and access it. In a easier way, there's something known as a hysteresis band. Your hysteresis band is equal to your upper trigger point minus your lower trigger point. And then you make two V supply into R1 divided by R1 plus R2. And in this case, your hysteresis band will be equal to 2 V supply into R1 by R2. Okay. So this is for your Schmitt trigger circuits. The derivations you can go through. It has been taught earlier in the session I have conducted also. LT spice demonstrations also have been provided also to verify these concepts. Now we will go to week 9. Week 9 is related to what is I like more called as data converters, which is ADC and DAC. Also, the sir has taught digital voltmeter. So what happens is, let us say you have a ramp which is going like this. And it goes like this, like this, like this, like this, like this. And you have some voltage which you want to measure. Okay. So you know 0 and Vmax. You know how much time this is taking. So if at this time I have a comparator and it is high over here and then it goes low over here. Again here it goes high, then again over here it will go low. So if I can measure this time, if this time is t measured, I can measure it. Then my V measured upon V max is equal to t measured upon t. In this way, I can estimate what is the voltage. So this is like a linear ramp type voltmeter. It will keep on giving this signal, a ramp signal. And at which instant it crosses it, I will note down. And how much time it is taking, I will note down. And depending on that, I can tell what is the measured value, measured voltage. Okay, so this is one way. Another way is you can have what is known as a this instead of being a ramp, it can be like a digital signal, like a staircase signal. Okay, like a staircase signal. So that is known as a linear ramp type, digital ramp type voltmeter, in which it is like a staircase waveform, and where it intersects, based on that you can measure the time. And how do you measure this time? This time there will be something known as a clock. There will be something known as a clock. This clock will be incrementing your counter. So your counter will say, let us say it counts till 100. And your clock is going at, let's say, 10 megahertz. The clock is 100 of 10 megahertz. So that means because your counter is 100, clock is 10 megahertz, your time measured will be equal to your clock time period into your number of counts. So it is 100 into 1 upon 10 megahertz. 10 to the 10 to the 6. So this will be 10 into 10 to the power minus 6. So this 10 microseconds. And let us say this time duration is, let us say, 30 microseconds. Right? And this Vmax, let us say it is 100. Or for simplicity, let us say 10. So your V measured is equal to what? T measured upon T into Vmax. That is 10 microsecond. Your time period is 30 microsecond. Into Vmax is 10 volt. So that comes out to be 10 by 3. So it is around 3.33 volt. Okay. It is around 3.33. So this is the way you use a linear ramp type voltmeter or a digital ramp type voltmeter. Next, we have what is known as a successive approximation registers, SAR ADC. Basically, ADC is like your digital voltmeter. It is getting your voltmeter in terms of a digital number. Okay, it is giving you the conversion and it is giving you the measured voltage. So now in a SAR ADC, what happens is, let us say we have a range. It can measure within, let us say 0 to 10 volt, it can measure. First, what it will do is, it will find a average of it. It will check whether it is between 0 to 5 volt. If the voltage which I have is within this range, it will consider this range. So now the new range which it will consider is 0 to 5 volt. Then it will find the half of it, 2.5 volt, and it will see where it is. Then it says it is between this range. Then it will focus between 2.5 and 5. Then it will find the half of it, 3.7. And say it finds it to be between here. It is between 3.75 and 5. Let us say it is found to be here. Then if we find a half of this, see, if we find a half of them and see where it is. Now it says it is over here. So that means what it is between 3.75 and 4.325 something. So then it will say it is between 3.75 and 4.325. So in this way, it is, you know, identifying what is the voltage. So it uses an algorithm that is similar to what is known as a binary search algorithm. So many of you will be confused, like what should I do? Should I proceed code or should I proceed software? And like some of you like to do both. And so you have come across binary search algorithm, which is a very famous algorithm, okay, and you have known what is the complexity of this algorithm, etc. Okay, so it works on the concept of this binary search algorithm. Next, okay. Then, so suppose it is an n-bit ADC. Okay, it is an n-bit ADC. So it will take n cycles. It will take n cycles to find it. Also, you must remember it will compare once at a time. So it will have it only requires one comparator. It is only required. This digital ramp type voltmeter, it will take 2 raised to n cycles. Okay, and this also has only one comparator. Another is known as what is known as a flash ADC. Flash ADC. So flash means works very fast. So here n cycles means it has to wait. You have to wait n cycles for it to tell you what is the voltage. So there's a delay. Flash ADC will have like multiple comparators. Like how you're comparing between 2.5 and 5. Then you're comparing between 3.75 and 5. Then you're comparing between 3.75 and 4.3 to 5. You have multiple comparison stages. But in your flash ADC, here you have like only one stage which is doing the comparison. But you're comparing with different values sequentially at a time. But in the flash ADC, we have many comparison stages, which will do the comparison at one shot and will give you what is which exact range is your voltage, and will give you that voltage. So flash ADC requires 2 raised to n comparators, and it is very fast to give you the value within one cycle. Okay, so this is the flash ADC. Next is there are DACs. DAC is the opposite. It will convert a digital value, it will give it to an analog value. Okay, digital to analog converter. There are two types. I'm not going into it for lack of time, but there's one is known as the R2R ladder, and another is known as you can make it using an adder circuit. Okay, and that is quite fast. It is usually quite fast as compared to the ADC. So ADC is the one which kind of acts like the delay, it brings a delay in the overall system. Okay, so next we'll go to week 10. So in the week 10, so consider what is known as an instrumentation app. It is a 2-stage amplifier, and it is made up of 3 op amps. Okay, these are R4, R3, R4. Your negative feedback comes. Use your VI1. Here again negative feedback goes. Use your VI2. Then from here, you connect it to R1. Here, connect it to R1. Again, you have this. And this plus. You have R2, which is connected down. You have R2. And your V output. Right? So your V output actually will be R4 by R3 into R2 by R1 into VI1 minus VI2. Okay. So This is the formula which you can get. Any queries? Okay. Then another thing was taught by sir, like how we are considered over here. We use what is known as these things. Okay, these things which we are rectifying our signal. We are rectifying the signal such that you can get a DC value, and from the DC value you can find out what is the average value. From the average value we can also find out the peak, and from the peak if we find out, then we can find out what is the RMS value, because the VRMS is equal to V peak upon V2, and this is only valid for what is known for a sine wave. This is only valid for a sine wave. So now if we want to do that also using op-amps, we can do it. We can say simple circuit where we have this here, this is your input signal, and this goes to a diode, and this is your R1, this is your R2, and here is your voltmeter. So this is to do a half-wave rectification. Do half-wave rectification. Okay. So next, we will go to week 11 now. I'm also getting a bit tired, but I hope this session has been useful for you all. So week 11, we will see there's something known as a combination. You have an integrator, and we have what is known as a Schmitt trigger. Both of these are present. Okay. So we know that the output Schmitt trigger is either positive or negative, right? Let me know. Okay. It is either positive, negative, positive, negative, positive, negative. So if it is generating what? So weak level is basically function level. Basically related to what is the function level. So generating a square wave. Now it comes to your integrator. Integrator, what it does, integrator will integrate, means it is basically adding. Suppose this is 10 volt, this is minus 10 volt. So you do 10 volt plus 10 volt plus 10 volt plus 10 volt, you give it to your integrator. Integrator will have a constant integration as well. So what happens is, integrator voltage will rise. And then again will fall, and will rise, will fall, will rise, will fall. So what you're getting a triangle. So using a combination of these two circuits, you're getting a square wave and you're getting a triangle wave. And this triangle wave is limited between the lower trigger point and the upper trigger point of your Schmitt trigger. Okay, it is limited between these two things, between the lower trigger point and the upper trigger point of your Schmitt trigger. Okay. So the weak level was basically related to the function generator, and also Sir touched regarding oscilloscopes. Oscilloscopes. So there are two types. One is the CRT, cathode ray tube. There are two voltages applied. Vx and Vy. Vx is your time-based signal, which is basically the signal. Okay. Vy is your signal which you want to measure. Basically sine wave or square wave or some random signal. That should be displayed. Like it should be seen by you. Okay, so that is why you use a cathode tube. So you connect two voltages and there's an electron beam which gets deflected according to voltage. So the Vx voltage is negative, positive, Vy voltage. Accordingly, it will change on the screen. Okay, where the beam is directed will change on the screen. Okay, so that is there. Then next is known as a DSO, which is a digital storage oscilloscope. Which uses multiple ADCs it will have, and they will sample the data and then finally it will show the data on the screen. Next is Lissajous plots, Lissajous curves. Okay, this is used when you do X versus Y plots, X versus Y plots, and over there, let us say you get a signal like this. Let us say this is your X-axis, Y-axis. You get a signal like this. Okay, there's something going like this. There is signal like this. Okay, this is your X-axis. This is your Y-axis. So what we do in that case is you have to count the number of, so this is most important. So you have to count the number of tangents. So you have to count the number of tangents. So here you will have your frequency of basically the Fy upon Fx is equal to the number of horizontal tangents upon the number of vertical tangents. In this way, you can find the ratio of frequency. So this was there a lot in your week 12 assignment. And I do feel that this is a method which you must know. And if I will, there's a link from which I have understood it in a better way, which was done by Rode and Schwartz, their company, which makes oscilloscopes. So I will post this link over here as well. Okay. So it is a link for the Rode and Schwartz thing which you can access. Right? You can learn more of the Lissajous branch. Next in week 12, so that's regarding BJT, regarding emitter, follower, voltmeter, so let's consider. So then what you must know in the BJT is this is your base, this is your collector, this is your emitter, right? So there's a drop VB. So you apply some voltage in the VN, right? And there's some resistor here. And if you measure the voltage over here, this will be VN minus VP. This will be what is now. So there is, it is kind of like a linear scale. Like say this is your V output, this is your V in. So it will start like it will go like this. This will be your curve. And this is your CV. Okay, so this is an emitter-follower voltmeter. So I also showed how we can use it to design a linear ohm meter. Also was shown. Okay, using a BJT circuit, how we can do it. Okay, so basically you have to know the fundamentals of the BJT. We know that the collector current is beta times IB, right? Your emitter current is IC plus IB. When we say emitter current is beta plus 1, IB, etc. And you have to know that your VB will be equal to 0.7 volt. And what is the range, etc. All these things were covered by some. Okay, so with this, I'll like to end the session. So if you have any questions, you can ask me or you can end it. So all the best. Okay. All the best for your exam. So I hope you guys have downloaded your admit card. You guys should have received an email for those who have registered for the exam. So you can download it and go to your center And I think your exam is this coming Sunday. So please prepare. So these notes are just a reference for you with some quick formulas so that you can use it in the exam. And please be very careful about the units. See the question properly, write down what is given, what is to be found, what is the formula you're using, and solve it with a calm mind. All right. So all the best. So do you have any questions you can ask, or else we can end the session. Okay, since there are no queries, I will end the session. Thank you for joining, and you can check out the YouTube video which will be uploaded soon, and you can ask your doubts over there as well. Right? Okay. So good night.